section, we discuss the invertibility of transition matrices. So we see whether the transition matrix or the transition matrices are invertible or not. We begin with an observation. Let V be a finite dimensional vector space, and suppose V equals V1, V2, etc. Vn be a basis for V. Then let us compute the transition matrix P B to B. So if there is no change in the basis, then what will be the matrix corresponding? So obviously it is identity matrix. So we have by writing the linear combination of the elements of B as the linear combination of elements of B itself, we have V1 equal to 1 into V1 and all other coefficient zeros. V2 equal to 0 V1 plus 0 1 V2 plus 0 V3 plus etc. plus 0 Vn etc. etc. Vn equal to 0 V1 plus etc. plus 0 Vn minus 1 plus 1 into Vn. Therefore the transition matrix from B to B itself is the identity matrix. So this is one crucial observation for the next theorem. So the first theorem is, let V be a finite dimensional vector space, and suppose that P is the transition matrix from a basis B1 to a basis B2. Then P is invertible, and P inverse is the transition matrix from B2 to B1. So very important theorem, that the transition matrices are always invertible, and if P is the transition matrix from B to B inverse, I mean B1 to B2, then P inverse will be the transition matrix from B2 to B1. Okay, so it has a simple proof. So it is enough to prove that. So what we have to prove is that P is invertible, and P where P is the transition matrix from B1 to B2, and P inverse is the transition matrix from B2 to B1, which is to be proved. So enough to prove that their product is the identity matrix. So we have to prove that P B1 to B2 into P B2 to B1 is identity. So what we do is we choose an arbitrary element from the vector space and prove that any arbitrary element is mapped onto itself under this product. So P B1 to B2 into P B2 to B1 into the matrix of V relative to B2 is equal to P B1 to B2 into P B1 B2 to B1 into matrix of V relative to B2. But in the previous class we discussed that P B2 to B1 into the matrix, the coordinate matrix of V relative to B2 is the coordinate matrix of V relative to B1. So we get P B1 to B2 into coordinate matrix of V relative to B1. It is nothing but the coordinate matrix of V relative to B2. So what we get is, for an arbitrary element V, P B1 to B2 into P B2 to B1 of the coordinate matrix of V relative to B2 is the coordinate matrix of V relative to B2 itself. Therefore, this product is the identity. So P B1 to B2 into P B2 to B1 is P B2 to B2 itself. That means V, the identity, I mean the coordinate matrix of V relative to B2 is mapped onto the coordinate vector of coordinate matrix of V relative to B2 itself for an arbitrary element V. Thus P B1 to B2 is invertible, and its inverse is P B2 to B1. That is a proof. So we have one remark from this. If B1, B2, B3 are bases for V, then P B2 to B3 into P B1 to B2 is equal to P B1 to B3. That is, if you change the base from B2 to B3 and then from B1 to B2. So if you take the product, B2 to B3 into B1 to B2 is the product. First we operate on P B1 to B2 and then we multiply to P B2 to B3. So the operation goes like this. We change the basis from B1 to B2, then from B2 to B3. So the resulting will be the change of matrix from B1 to B3. Okay, that is P B2 to B3 into P B1 to B2 is equal to P B1 to B3. Now let us, so our problem is to evaluate or compute the transition matrices for Rn. So let us assume B1 and B2 be two bases for Rn. And P P B1 to B2 is obtained by expressing each element of B2 as a linear combination of the elements in B2. Each element of B1 as a linear combination of the elements in B2, which will result in a system of n linear equations, and not only a system, it will result in n linear systems of n equations in n unknowns. So you just go back to the previous problems where just a single vector gives n number of linear equations. Say if it is on R3, then a particular element x, y, z of R3 will give you 3 linear equations. We have done certain problems. So this will result in an n linear system of equations of it will result in n linear system of n equations in n unknowns. So note that I have made a mistake by repeating the word systems. Each of it has the same coefficient matrix. That is a very important point. And this may be represented as ax1 b equal to b1, ax2 equal to b2, etc., axn equal to bn. Then p b1 to b2 is invertible. Therefore, the transition matrices can be found by the following procedure. So the procedure is, we follow a 4-step procedure. Step 1, form the matrix. So if you change from B1 to B2, you form an augmented matrix where the first part is B2 and the second part is B1. So form that matrix and you row reduce to echelon form. The first matrix B2 is row reduced to echelon form. Then the resulting matrix will be, the first will be identity and the second will be the required matrix, the transition matrix P B1 to B2, and you extract just P B1 to B2 from that particular matrix. Okay, so we will discuss an example regarding this. So what we do is, we will write the augmented matrix where the first part is the new basis and the second part is the old basis, and row reduce where until the first matrix becomes identity. Then the second one will be the required transition matrix. Second theorem, let V1, V2, etc. Vn be a basis for Rn, and S is the standard basis for Rn. Then if the vectors in the basis B are written in column form, then the transition matrix from B to S has columns V1, V2, etc. Vn. It is just an observation from the previous theorem and this procedure. So as a remark, if A equal to the matrix V1, V2, etc. Vn, where each V1, V2, etc. are a column matrix, if this A is invertible, then we can view A as the transition matrix from the basis V1, V2, etc. to the standard basis for Rn. So we have an illustrative example. Let B1 and B2 be two bases for R2, where B1 equal to set ordered pairs 1, 2, 2, 3, and B2 equal to the set of ordered pairs 1, 3, 1, 4. Using the method of row operations, compute the transition matrices from B2 to B1 and then B1 to B2, and verify that they are inverses of one another. And given a vector W equal to 0, 1, find its matrix, coordinate matrix relative to B1, and using that particular matrix and the transition matrix from B2 to B1, find the matrix of coordinate matrix of W relative to B1. And same problem where B1 is replaced with B2. So first we compute the transition matrix from B2 to B1. So what we do is, as in the procedure, we will make an augmented matrix in which the first part is the new basis and the second part is the old basis. So we have the matrix 1, 2, 2, 3 as the first part, and second part is 1, 1, 3, 4. Row reduced operations will give you 1, 0, 0, 1 as the first part, and the second part is 3, 5, minus 1, minus 2, which is the required transition matrix. Similarly, we can do the other one also. and just by multiplication we can see that one is the inverse of the other. Then finally let W equal to AU1 plus BU2, so that the matrix of W, coordinate matrix of W relative to B1 is 2 comma minus 1. This is 2 comma minus 1 in the sense it is the column vector. We have already discussed in the previous class. Thus, the matrix of W relative to B2 is P, the transition matrix from B1 to B2 into the coordinate vector of W relative to B1, and you get it as minus 1, minus 1. In the same way, you have another vector 2 comma 5 with respect to B2, its coordinate vector is 3 comma minus 1, and the coordinate vector relative to B1 is 4 comma minus 1. Thank you.